You just want Dr. Fahey? You don't want Jed Fahey? All right.
Jed.
All right.
They'll subtitle it if they want.
Yeah. So, Dr. Fahey, you spent...
Jed, please, Patrick.
Oh, okay, sure. Jed. So you spent over 30 years working at Johns Hopkins University and another 15 before that working with phytochemicals. What is it about whole cell microalgae, specifically its delivery system for the omega-3s? Why is that an attractive nutritional component?
We have to look at the broad picture, I think, and I've been trying to do that throughout my career, although as a scientist, yes, I wound up studying individual phytochemicals separately. But when we think of phytochemicals, and after all, algae are plants, microalgae are plants, and they have a lot of phytochemicals. Phytochemicals are beneficial for humans by definition. Yes, there are some plants that have toxins, and those are toxic plants and we don't eat them, or poisonous plants.
Right.
But beneficial plants, which we're talking about, microalgae that produce omega-3s and DHAs, produce a lot of phytochemicals, including the omega-3s like DHA and EPA. But it's that whole package of hundreds, maybe thousands of phytochemicals that all come through in this whole cell delivery system. We're not smart enough yet as scientists and as statisticians to understand how to make complete sense of the synergy, the 1 + 1 = 3, not 2, of different phytochemicals together. So one of the things we do know, though, is that the DHA coming through in those whole cells, whatever the algae made, remains pretty much that way when you deliver it as a whole cell. It doesn't get photooxidized. It doesn't get oxidized by heat, which happens in the extraction process when you extract fish oil. And it's complemented by hundreds, probably thousands of other phytochemicals that are in that same algae. And we know that there is protection going on. There's probably synergy or more than additive effects. This is maybe an opportunity for me to remind whoever's listening and whoever's interested that the estimate of the number of phytochemicals present in the plant world now is over 5 million. A few short years ago, the estimate was maybe 50,000. So, okay, we don't know exactly how many, but there are a boatload of them. And any individual species of plant has hundreds, perhaps thousands of them.
So specific to microalgae, are there
Yep,
any
yep.
phytochemicals that come to mind in terms of health benefits that may be already out there in the literature and somewhat known, but that we can speak to so people may become more aware?
Yeah, the most recognizable ones are the pigments like astaxanthin, which is certainly beneficial. A lot of these pigments that make algae and other plants green or orange and yellow, various colors, are pigments that are, because they have to resist the degradative effects of light exposure and heat, they're resistant to oxidation, and many of them themselves are antioxidants. So astaxanthin is a good example of it. So yeah, there are many phytochemicals, which are, by definition are small molecules. They're not the enzymes, the proteins, the carbohydrates, the starch, the oils, or the fats that are called macronutrients.
Yes.
They're not the vitamins and minerals, which everybody's familiar with, at least by name. They're all the other stuff. Yeah.
Right.
There's a lot of that other stuff.
There's a lot, yes.
Yeah.
Why are omega-3s so important to nutrition for humans and animals?
So people use the word omega-3s in the supplement industry all the time, nutritionists and dietitians. I think it's fair to say not everybody knows really what that means. So an omega-3 fatty acid is, as you know, Patrick, is just, it's a long chain, it's a fatty acid of some chain length that has some double bonds in it or not. And so the naming of omega-3 fatty acid means it's a chain of carbon molecules, and 3 carbons after one end of that chain, there's a double bond. That's all that means. So you have ALA, or alpha linoleic acid, that has 18 carbons in the chain.
Right.
You have EPA, that has 20 carbons in the chain. You have DHA that has 22 carbons in the chain, and they have respectively 3, 5, and 6 double bonds that start 3 from one end and then alternate and go up the chain. Way too complicated for a non-scientist, but why does that matter? It matters because your body, which has something like 40% of the unsaturated fatty acids in the brain as DHA. Your body needs DHA, and it can't make it. It can't make it itself because the interconversions of lipids, fatty acids, sort of only go so far with the enzymes that the human body has.
Right.
So it can't take a fatty acid like linoleic acid or a shorter chain fatty acid from plants, and it can't convert it to the DHA that it needs. So that's why it's important to supplement with DHA. And I talk about it from the clinical human perspective, which is where most of the research has been done. But certainly we know that dogs and cats and companion animals, fish, for that matter, all of them require DHA for the brain, among other things. And I'd like to talk with you also about how that DHA is used in those organs.
I'd love to talk about that. Yeah.
Okay.
So there's two primary places that you find omega-3, particularly DHA, within algae cells.
Mm-hmm.
And one of those is in the cell wall, and the other is in a vacuole or sort of an energy storage sac. Now, the energy storage sac is usually triglyceride forms of DHA, primarily used for energy. Mm-hmm. Within the cell wall, you'll have phospholipid DHA, and this is incredibly important to the cell wall. It helps with membrane fluidity, which, as you know, will help with protein function on the surface of the cell wall or within the cell wall. So that'll help things like cell signaling and passage of materials in and out of the cell. So the same reason why algae cells have that phospholipid DHA within their membrane is the same reason why we need phospholipid DHA within our membranes. It's still involved in membrane fluidity and cell function. If you're deficient in DHA, as many people are, because you mentioned poor conversion rate from other fatty acids, we have a terrible time synthesizing it. But if you're deficient in DHA, your body will still make new cells and they will still have cell walls. The difference being, instead of using phospholipid DHA in those cell walls, it'll have to resort to using omega-6s or other molecules that are more rigid. Mm-hmm. And so this will decrease cellular function because your cell surface proteins won't be able to interact very well. And it can lead to some serious health consequences.
I'm glad you brought up, excuse me, the issue of membrane fluidity. This is something that matters in all creatures, certainly in all animals and plants, higher and lower, that for membranes to do their function. So cell membranes, as you mentioned, are just beneath the cell wall and the outside of plant cells, and in animal cells there is no cell wall to protect them, but they are like the skin of a balloon. But they're like the skin of a balloon that allows certain stuff in and certain stuff out, and in fact has enzymes that are little islands, if you will, in that balloon skin, can actively move specific things in and out. And this has to do with energy and all sorts of functions, energy generation. So if those balloon skins are not fluid enough, you run into huge trouble. It's as if you, I don't know if this is a good analogy, but if you put a balloon in a deep freeze and take it out and touch it, it's going to shatter or burst. Similar, but obviously not identical phenomenon in cells. And so taking it back to the functional aspect of it, I personally don't know why it makes coats and hair glossier. You may have some insight into that, but in the brain, what is the brain? The brain is a bucket of fat. It's 10 or 12 pounds in humans. It's obviously less in animals. And the fat is, as I said earlier, 40% DHA, more like 20 to 30% DHA in total. But Where it occurs is in the cells of the brain. What are the cells in the brain? They're basically neurons. And the critical function of DHA in brain cells is in the synapses
Yes.
between nerve cells. So it's critical for transmission of nerve impulses. What does that mean if you don't get enough DHA as you're developing or as you're thriving later in life? It means potential neurodegenerative, higher rates or more rapid onset of neurodegenerative conditions. Certainly if you don't get it in utero and as you're developing, everybody's heard the first 3 years of life, the first 1,000 days are critical. Well, it turns out that DHA levels are constantly growing in a developing brain and don't plateau until about 18 years of age. That's, again, in humans. Dog years divided by 7, do the math.
Yes.
But for better or for worse, a lot of that work was done either with humans or with small animals like mice.
Yes.
Very little has been done with cats and dogs. We know it's the same.
Yes, we understand the function.
Yeah.
Yes.
Yeah.
Yes. I like that. So when I was doing some research for this, and I was trying to talk about cell wall and how, or membrane fluidity and phospholipid DHA, it sort of occurred to me when it led to the next, my next thoughts was why they have such a hard time concentrating phospholipid DHA from extracted fish, krill, or algae. And it makes perfect sense after I read that. I'm like, well, they strip the cell wall and they throw that part away. So they're left with a very small amount of that phospholipid DHA and mostly triglyceride DHA. And then it brought me to their concentration process where they take the triglyceride DHA, they remove the head of the molecule, the glycerol, they add an ethanol in. They do that so they can fit more in a pill. Mm-hmm. But by doing that, you've reduced the bioavailability again and made it more prone to oxidation. So it was nice to have those points lined right up while I was doing my research. I enjoyed that.
Yeah, well, we denigrate or criticize commercially extracted fish oils, and well, we should, in my opinion.
Yeah.
But I think it's important to stress, and there's research on this, that processing of these fish oils does, and the packaging and the sale of it actually does open up a huge pathway to degradation, and that's what happens. And I've read recently that something like this is after you cook fish, something like 85% of the DHA is oxidized, is basically lost to. Two things happen. It's lost to your use. It's degraded. It's oxidized by the heat of cooking, but it also means that there are toxic oxidation products, LOPs or lipid oxidation products, and reactive oxygen species or ROS. These acronyms are used even in marketing literature.
Yeah.
So you've got a sort of double whammy of bad stuff happening. And certainly, and again, I've read this, I haven't done the studies myself, something like 85% loss of DHA when you fry fish or deep fry it. And it's less, but it's still not less than 30, 40, 50% if you poach or bake or steam fish. Yeah. And yes, there's a difference in loss and oxidation between different species of fish. If you're looking to get your DHA from eating fish, if you're eating sushi, I guess one could make the case that you're getting more of it.
Yeah.
Not all of us eat sushi all the time in the West. I love it, it's delicious, but I can't afford to eat it all the time.
Yes.
So bottom line is most of us are eating cooked fish, and there's a huge loss of degradation.
I think they have a hard time quantifying the loss because through the oxidation process, you may have that omega-3 molecule degrade, and unfortunately, the molecule degrades, but the backbone stays the same. And so you're able to claim on, say, a label or a pound of fish there is X amount of omega-3 in this, but there's no way to quantify whether or not that omega-3 has or has not been oxidized and whether or not it maintains its functionality. There are ways to test for oxidation in products. You can test for the downstream products of the omega-3 oxidation. They won't directly quantify your omega-3's level of oxidation, but if you're making that analysis on an oil, there's nothing else there to oxidize. So unfortunately with those tests, they're done during manufacturing, pre-packaging. And the industry will say, we're within acceptable standards and we'll send this product out, but then it sits in a shipping facility, it sits on a shelf, and independent research has shown that over 50% of the products that are on shelves are oxidized above industry level standards before you open the package. So it's tricky to quantify oxidation within products, especially with extracted oils.
I don't know if there is a protocol in the industry that recommends how to store fish oils. If I were taking fish oils that I bought from someplace other than from the manufacturer, not Amazon, where it will be sitting on a shelf in a warehouse, I would want to have an inert gas like nitrogen or argon that I would flush the bottle with every time I opened it.
Yeah.
Obviously, my house isn't set up to do that.
Yes.
And I would want to store it in a freezer.
Yes.
And I would want it to see no light. And we know that all of those things, oxygen in the air, light, and heat, tank the DHA content and EPA content of extracted fish oils rapidly. Certainly over the course of a month, if someone buys a fish oil supplement and taps it every day for a month or so. So that's over and above what you mentioned of the hazards of manufacturing it, having it, even with a short shelf life, having it sit in a warehouse, distribution, postal service, shops, however it gets to the consumer.
Good points, Jed.